this video, I will be explaining the first of the Newton codes, formulas for numerical integration, namely the trapezoidal rule. So the trapezoidal rule, like I said, is the first of the Newton codes formulas, and they correspond to the case in which your approximating polynomial is of the first degree. Recall that this was the general formula for the Newton codes formulas. You approximate this function f of x with a polynomial f1 of x or fn of x, and in this case it is a first order polynomial, so it's f1 of x. And recall from the Newton interpolation video that we can represent a first order polynomial in this way if we have these data points at axis A and axis B, and then we can integrate this first order polynomial to obtain this equation for the approximate integral. So this is the final expression for the trapezoidal rule. So graphically, the trapezoidal rule corresponds to approximating the area of the trapezoid under the straight line connecting this f of A and f of B, these two data points. So you can see that that is depicted in this figure here. You'll have your first order polynomial, your straight line that passes through the two data points, and your integral is going to be the area underneath this straight line. So what is the error in this method? Well, we have a local truncation error, so that means the error that is associated with a single application of the trapezoidal rule over a single interval. And this is given by this expression. E is minus 1 over 12 times this second derivative of f of xi times b minus a to the third, where xi is some value that is in the domain of the integral, so somewhere in between a and b. So we can see that this error depends on the second derivative of the function f, and therefore if you have a function that is of degree 1 or less, your error is going to be equal to 0 because your second derivative is equal to 0, and your estimate of the integral is going to be exact. This makes sense because in this case, if your second derivative is 0, you will be having a function that is a straight line, and if you approximate it using a straight line, then there is no difference. However, if there is some curvature in the function that you want to integrate, you will have some error. But we can say in general this single application of the trapezoidal rule is therefore first order accurate. So in order to improve accuracy, you can apply the trapezoidal rule multiple times. So we will divide this whole interval into different segments and apply the rule for each segment. So in this case, you will approximate the function using a number of straight lines. You'll calculate the area of the trapezoid for each segment, and this is depicted in the figure as well. In figure A, you divide the interval into 2 segments, figure B 3 segments, and it goes on and on. And as you can see, the integral becomes, or the area under the approximated functions becomes closer and closer to the actual integral. So we can say that we divide the interval into n equally spaced segments with a width of h. Therefore the expression of h is going to be b minus a, so the end and start point of the interval, divided by n. And if we do this, we will have n plus 1 base points that are given in this way. So we'll have the start point A, which we can also call x naught. Then we'll have x1 up until xn, and the endpoint xn we also called b. So then we can rewrite the integral to be the summation of each of the integral of each of these segments. And then we will substitute the trapezoidal rule for each of these integrals that we had in this last expression. So then we obtain this summation. You can see I is approximately equal to h over 2 times this f of xi minus 1 plus f of xi, where I ranges from 1 to n. And this is the general expression for the composite trapezoidal rule. So we already discussed the error in a single application of this rule. So what is the truncation error if we apply it over n segments? So we can calculate the global error, the global truncation error, by summing the local errors for each segment. So then we obtain this equation. So in the first expression, you'll see it's just the sum of the local errors. Then you can substitute the expression that we have for h is b minus a over n, into this equation. And then we can rewrite it to get this bracketed expression, which is sort of an average value of the second derivative of f over this domain. And we can now apply the discrete mean value theorem to this. And this states that there exists xi on the domain from A to B, such that this average, so the sum of I is 1 to n of this second derivative of f of xi I over n, so the average, is going to be equal to or to the second derivative of f of xi. So then we can substitute that into the expression of the last slide to get this global error. Global truncation error is this for some xi on this interval. So now what we can do with this is we can say that we can bound our error by the maximum expression of this error. So here you see the error is smaller or equal to b minus a to the third over 12n squared, multiplied with the maximum value that the second derivative of f of xi obtains over this interval from a to b. Yes, so again, this was the error, the composite trapezoidal rule. And you can see that it scales with 1 over n squared, or with h squared, alternatively. And therefore we can say this. So the error term depends on h squared. So we'll have big O of h squared. So now let us apply the trapezoidal rule to an example problem. So here we want to find, to estimate the integral of this function 3x times the exponential function of minus x over this interval from 0 to 2. And we're going to use the trapezoidal rule with 4 segments. First we can analytically calculate this integral. Obviously, if you apply this method to a real-world problem, you often cannot solve it analytically, but we can to sort of compare the errors, to compare the approximation still. So then we obtain this value, and we obtain this plot of the function. So now let us solve this numerically. So we have these values of a, b, and n, and then we can calculate the step size h, which is going to be 0.5, and then we can determine our base points. So again, we have 4 data points, or with n is 4, so we'll have 5 base points, and they are given by this. We can plug those into this function that is to be integrated to obtain these values of f of x. Then we can plug in those values of the base points into this summation to obtain the integral with the trapezoidal rule. So this is what we do in the second step here, is we just plug in the values and we get this estimated integral of 1.7118. And again, we graph this, we plot this in MATLAB. So we have the actual function, and we have our base points given by the black dots, and we have straight lines connecting the base points. And the integral that we just calculated with the trapezoidal rule corresponds to the area of the red surface. So the difference between our estimated value and the integral that we solved analytically is given here. We can also use the estimated error bounds, so the estimated truncation error that we just gave a general expression for a couple slides back. So we saw that this error was smaller or equal to this expression, and for this we calculate the second derivative of the function that was to be integrated, and we found that the error was bounded by 0.25. So indeed we can see that the error that we obtained using our trapezoidal method is indeed smaller than the upper boundary of the estimated error. So yeah, the trapezoidal rule, some limitations of it. It can require a lot of computational power when you need to obtain a high accuracy and low error in your integral, because you will need to divide your interval into lots of segments with a small step size h. So instead, another way to improve efficiency is to use higher order polynomials instead to approximate the function that is to be integrated. And then we come to the higher order Newton-Cotes formulas that I will be discussing in the next video, which are the Simpson's rules.